this is homework 6, group 3, Nurato Denara, section 1, number 6. Exercise A. In this exercise, we need to find how many students are taking both English and math subjects. First of all, we find the formula to find the intersection of E and M. Then we find the union of E and M and take it to the formula and find the intersection of E and M. And it is exactly how many students are taking both English and math. It is 35. Then exercise B. In B exercise, we need to find how many students taking math and how many students taking English. So first of all, we identify X as math subject and Y as both subjects. And find how many students taking only English and only math, and making the formula of how many students taking only one of subjects. Then we find how many students taking at least one subject. It is 82, and we also make formula. Then we trying to solve this system and find X. How many students are taking math. It is 37. And then as we said before, English is 74 students, because English is 2 times more than math students. Number 9, exercise A. We need to find how many people bought at all 4 juices. There is no one who bought all juices, because none of these items explicitly specify all 4 juices. Exercise B. Who bought only grapefruit juice. At all, people who bought grapefruit juice are 100, and we find how many grapefruit juice bought with other juices, and then by formula find that grapefruit juice only bought only 35 people. Then exercise C. In exercise C, we need to find who bought exactly 2 kinds of juice, and first of all, we need to find who bought 2 kinds of juice and take from them who bought this kind of juices with another one kind, and then where is non-negative numbers, we sum them, and there is who bought exactly 2 types of juice. In side C, we need to find who bought more than 2 kinds of juice, and we just sum peoples who bought more than 2 juices. It is all 3, because there is no who bought only all the 4 juices, and it is 32. Number 12, exercise A. First of all, we need to divide the number to multipliers, prime numbers, and then by formula we need to find how many numbers less than given number are relatively prime to given number. It is 200 numbers, integers, that less than 500 are relatively prime to 500. Big exercise. We need to do the same one and find that there is 4,320 integers that are less than 9,975 are relatively prime to this number.
Palindrome. A 5-letter palindrome consists of 2 identical letters at the beginning and the end, 2 identical letters in the second and fourth position, and 1 letter in the middle. The first, second, and third letters can be any letter, and the rest is determined automatically. 8-letter palindrome, and 8-letter palindrome is similar to the previous one, but it has 4 pairs of identical letters. The first and the last letters are identical, the second and second to last are identical, and so on for all the pairs. Palindrome with lengths from 1 to 8. We calculate the number of palindromes for a length from 1 to 8. Each palindrome follows a similar structure as in A and B, but for different lengths. 15-letter palindrome. 15-letter palindrome consists of 7 identical letters. and the rest are automatically determined as the need to match the letters opposite them. Problem 10 explanation. For the first two digits, there are 8 possible choices. Since the digits can be 2, 3, 4, any number, 8, 9, the third digit has 9 possible choices. It can be any number from 1 to 9. For the last 4 digits, each has 10 possible choices, since they can be any number from 0 to 9. To find the total of possible telephone numbers, we multiply with the numbers of choices for each digit, 8, 8, 9, 9, 9, 9. Problem 12, explanation. An 8-to-8 chessboard has 64 squares, but we are looking for pairs of adjacent squares. Adjacent squares can be either horizontal or vertical adjective. Horizontal adjacent squares, each row has 8 squares, so there are 7 pairs of adjacent squares in each row. Since there are 8 rows, the total number of horizontal adjacent pairs is 8 multiplied by 7 equal to 56. Vertical adjacent squares, each column has 8 squares, so there are 7 pairs of adjacent squares in each column. Since there are 8 columns, the total number of vertical adjacent pairs is 8 multiplied by 7 equal to 56. The total number of adjacent pairs, both horizontal and vertical, is the sum of horizontal and vertical pairs.
Let's solve chapter 3 problems. A. Both numbers are equal to 2. That has one outcome. So our answer is 1/36. B. Total is at most 10. That has 3 outcomes. We need to take down 3 and our answer is 33/36, which equals 11/12. C. Both are factors of 70 whose product divides 70. That has 7 outcomes. So our answer is 7/36. D. Numbers add to a number divisible by 5. That has also 7 outcomes. So our answer is 7/36. Problem 5. Problem 5. Total outcomes equals 64. A. No heads just equals 1/64. B. Exactly 2 heads, which equals 15. So our answer is 15/64. C. At most 2 heads, so which equals 22. So our answer is 22/64, which equals 11/32. D. At most 5 heads. We need to take down 1, 6, and 6. So our answer is 63. So final answer is 63/64. E. Odd number of heads. We need to product our odd numbers, so which equals 32. Our answer is 32/64, which equals 1/2. Now we're gonna solve problem 12. We have 5 red balls, 4 white balls, and 3 blue balls. In total, we have 12 balls. A. We need 2 blue balls, which equals 3. So our final answer is 3/66. B. At most 1 blue ball. We need to take down 3, and our answer is 63. So our final answer is 63/66. C. At least 1 blue ball. We need to take down 36, which equals at least 1 blue ball. So our final answer equals 30/66. D. A blue ball and a white ball. We need to multiply a blue ball and a white ball. So our final answer equals 12. So our answer is 12/66, which equals 2/11. E. Either at least 1 blue ball or at least 1 white ball. Our variable equals at least blue plus at least white, and in final we're gonna take down both. So our answer equals 56/66, which equals.
My name is Kasim Turar. I'm from BDA 2404, Group 3, Discrete Mathematics. I'm solving 2 exercises, exercise 15 from section 2. The exercise says how many three-digit numbers contain both 2 and 5, but not all 0, 3, and 7. So allowed digits is 1, 2, 3, 1, 2, 4, 5, 6, 8, 9. Numbers must contain 2 and 5. Should appear at least once. Third digit can be any number from allowed set. So we need to satisfy three conditions. Condition number 1, 2 2s and 1 5. It's three numbers. Condition 2 is 2 5s and 1 2. It's also three numbers. And 1 2 and 5, but over third digit it can be any digit from allowed set. It's 1, 4, 6, 8, 9. For each third different digit, it's factorial 3 equals 6, and there is 5 allowed digits, so 6 times 5 equals 30 numbers. So we have 36 digits in total. So it's 36 digits that contains 2 and 5 and don't contain 0, 3, and 7. Section 3, exercise 20. There is a set of several numbers. It's 8 prime numbers less than 20. In part A, we have this set of 8 prime numbers. How many non-empty subsets of S have the same sum? There are 256 total subsets. Since we ignore the empty set, we have 255 non-empty subsets. The smallest sum is 2 and the largest sum is 77. Adding them all together, these numbers, that's sum from 2 and 2, 77 or 76 possible sums. We're putting 255 sums into 76 possible sums by pigeonhole principle. At least one sum must appear in at least 4 different subsets. So there are at least 4 subsets with the same sum. Part B. What about products? Can different subsets multiply to the same number? We need to determine 2 non-empty subsets have the same product. Every product is built by multiplying unique primes, and by the fundamental theorem of arithmetics, every number's factorization is unique. But no over combination of these prime numbers makes 6. For example, set of 2 and 3, 2 times 3 is equal 6, and for example, set of 3 and 2 have the same product of 6. And so every integer greater than 1 has a unique prime factorization. Since all elements of S, set S, are distinct primes, the product of any subset is unique. So no all non-empty subsets have distinct products.
Review section of chapter 6. Exercise 3. A palindrome is a word, number, or sequence that reads the same forward and backward. The author named John Sununu reminds of a palindrome because of the repetition and symmetry of non-VZ. B. 7-letter palindrome have the form ABCDCBA. So the palindrome is determined by letters ABCD for positions. We need the letters to include S and use at most 3 different letters. So the total number of such 4 letter combinations include S used at most 3 distinct letters in total. So let's count. So total is 11,151. C. For all 7 letter palindromes, again of form ABCD CBA, you only choose ABCD freely from 26 letters. So total is 26 in 4 degree. It's 456,976. D. 7 letter palindromes with at most 3 different letters, one of which is S. Total case for 1 letter, 2 letter, and 3 letter combination, including S like in B, but general not restricted to 4 positions. Still governed by letters A, B, C, D, so similar logic as in B, but for all combinations with less or equal 3 letters, including S. Total is a subset of C, around 11,151. E. A palindromic rock band of the late 1970s, still popular today, is ABBA. Exercise 4. A 9-letter palindrome has the form A, B, C, D, E, D, C, B, A. Symmetric middle letter in is E. A 10-letter palindrome has the form A, B, C, D, E, E, D, C, B, A, determined by first 5 letters. So both 9-letter and 10-letter palindromes are determined by 5 characters. There are exactly the same number of palindromes of each kind. So the second student is right, the number is the same in both cases. Exercise 10. By dividing the triangle into 9 regions of side length 1 divided by 3 and applying the pigeonhole principle, we guarantee that at least one region contains 2 points, which must be at most 1 divided 3 units apart. So thus the statement has been proven.